Yeah, so that was a great lead in from Timothy and a great discussion as well. We'll have a little bit of overlap here, obviously, but I'll do my best to be light with it, but also sort of share my spin on my aspects of the project as well. So I was one of the individuals who's been involved pretty much since the early days in 2015 with sort of the puppy harness. And more recently, we've been moving into, as Timothy mentioned, the second phase of raising the dogs with these collars. So I'm going to talk to you today about ECG and respiration signal reconstruction from the IMU at various orientations during rest or sleep and utilizing this for dog welfare monitoring. So I'm Mark Foster. By the way, just to clarify, I work closely with George Wang from Dr. Roberts' lab, Evan Williams from Dr. Bozkurt's lab, and Dr. Roberts and Bozkurt as well. So a little bit, just a high-level outline of what we're going to walk through here. So the motivation for the work that I'm doing, that we are doing, trying to reconstruct these signals, and a little bit about our research partner from the hardware perspective and the signals that we're collecting. I'm going to discuss first our proof of concept and the methods and results with this, and how we've expanded this study into further methods, the results of those, and then finally talk about what the impacts and future work for this project will be. So Timothy covered a lot of this. Just wanted to hit on that there's a large number of people with visual disabilities in the US, and there's definitely a shortage in the number of guide dogs available. This is partly due to training, partly due to availability. It's incredibly expensive the longer the dog remains in the program. So the earlier you can identify success of the dog or necessitates a career change, the better off it'll be for the program. It takes about 2 years to train the dog, and then they have an average working time of 6 years. Guide dogs is definitely one of the most difficult careers to train for. These dogs are really a lifeline, and they work in a symbiotic relationship with their handlers. They provide them freedom. These dogs are just incredibly important. An interesting behavior that I always think about that's different with these dogs from other careers is this willful disobedience that's needed. The dog needs to lead. In other professions, the dog can execute commands, but if their partner asks them to cross the street, the dog needs to have willful disobedience to say, no, we're not crossing the street right now. It's not safe. So these dogs are incredibly important. They're working under stressful environments, working with their handlers every day. So we're responsible for the welfare of these dogs as humans. And as research partners, we want to focus on the welfare of these dogs and how we can help them. So our partners with Guiding Eyes, as Timothy mentioned and Dr. Bozkurt mentioned in the discussion, it's a large nonprofit organization. They graduate 160 dogs per year. There's a pretty intense matching process where they're really trying to match the dogs with the handlers. So that's why it's so important to get all this longitudinal information about the dogs. As you can draw these conclusions, looking longer term as we collect more information about what dogs become successful, and then what pairs become successful as well. Guiding Eyes is a great partner for us. They collect extensive data related to their raising program with genetics, their temperament testing, as well as with their pairing, as I talked about. So a lot of that work goes on site. So our goal with our research partnership is to enhance our research efforts to aid in the training and development of the guide dogs. So the first aspect of hardware we developed that Timothy mentioned on that graph is early on. So at 8 weeks, we developed a puppy harness. So it measures the heart rate and activity during the first puppy test. And as Dr. Roberts mentioned, we're starting to see early outcomes. There is a gap in the data due to COVID, but they've been ramping up. So we're finding that we can make some predictions related to the experts' scores using heart rate and activity level. So these are definitely items of interest for us. In the second phase of the raising, the dogs, as Timothy mentioned, are removed from Guiding Eyes supervision. So they're no longer at the site. We've developed this smart collar, which has sensors primarily for the environmental and behavioral monitoring. However, looking at our role and our purpose here is to also monitor the welfare of the dogs. So looking into the research, into the literature and what's possible, it is possible to get some heart rate information from an IMU with the dog. So our goal was to take this collar and see if it's possible to get physiological parameters as well. As mentioned, we're tightly involved with guiding eyes. So we're working in that 8-week span as well as that long span. So there are collars that exist, smart collars that exist. However, in order to build this longitudinal database, we want to have access to raw data and track the dog specific to the program with everything in one place. So there was a need for us to develop our own system. So the experimental overview and our motivation was to try to monitor these guide dogs' physiological parameters during sleep or restful times. So these dogs are with the razors, they have the collars. This is an opportunity for us to get more involved and try to monitor their welfare. So in the initial experiment, in this experiment, we're gonna outfit the dog with our custom collar, which has the IMU, used commercial sensors that are validated for benchmarking for the heart rate and respiration rate. I'm going to move the collar around to different orientations as the dog sleeps. And it's worth noting that all our animal procedures were approved by NC State Institutional Animal Care and Use Committee. And the results we're going to have is we're going to extract the heart rate from the IMU signal as well as our respiration rate. So the initial objective was simply a proof of concept. It was, can we extract the heart and respiration rate from our sleeping dog using the IMU and validate these against commercial ECG? Looking into the literature, there's examples of getting the heart rate from the IMU, but not the respiration rate from a dog at rest. So our gold standard, our reference was these Vernier devices. Vernier, they're very nice, but they're impractical. They're good for benchmarking. They're a little large. They're about the size of a credit card. So good for proving our concept, but not practical for long-term wear of the dog. So initially the dog was in a single position on his right side, and we're just moving the orientation of the IMU to try to see if we can get the heart rate. So put it in one specific location in one sleeping position. So used a semi-automated detection with it in one position, aligned our ECG data from the IMU along with the standard system, and then processed a single axis on this IMU signal. So we resampled it and bandpass filtered it, took the derivative to get these peaks, and windowed it to try to do peak detection. So the initial results were pretty good from this single orientation and single position. So overall, there's an F1 of about 0.86. You see in the middle there how the data gets lined up. So the pulse wave of the IMU is actually delayed from the ECG. The ECG is going to be an instantaneous measurement, and we see that constant delay because the collar is in a fixed position. In the bottom right, in the blue, is that ECG signal. So that's more of a typical PQRS wave. And the orange is the IMU signal. So that's looking at a pulse wave. So you're not getting all of the heart information, but you can extract the heart rate from that singular peak. So from that same data stream, we're also able to estimate the respiration rate. So again, we align the IMU data with the respiration data and then process that single axis again. This is going to be a lower frequency wave as the respiration rate is going to be lower compared to the heart rate. So on average, it was an accuracy of about 94%, but there was some low accuracy ranges, which is mainly just due to the small number of breaths that occur per minute. If there's only 15 or 16 breaths per minute and you're off by 2, it could be an 80% accuracy. But overall, we're in the right ballpark, we're in the right window. You can see in the graph here. The blue is the standard respiration sensor, which is a strain sensor on the chest of the dog, and in the orange is our IMU sensor. So this was a nice experiment. It proved our proof of concept that this could be done in a single position with a single location. But this is not going to be practical long-term, so we need to build on this experiment. So the next phase of the experiment, this is my dog. He's trained to sort of sleep on his right side and wear the equipment. So I was able to leave him in one position. So we're just going to change one variable at a time. This time I'm going to expand the study by rotating the collar around the neck. When the dog is sleeping at night, the collar is going to be free to rotate. So I separated the collar position into 12 different positions, much like you would around a clock, collected 3 2-minute data sets for each position, which gave me about 100 beats per minute per data set. So looking at the setup down here for the position, so I noted the equator. So the equator I define as basically the spine to the throat across the dog. at 12 and 6, and then 3 is on the top of the dog. So that was where the initial experiment was performed. And then position 9 would be between the dog's neck and the lying surface on the right-hand side. So we had to create a pipeline in order to understand, number one, what position the collar was going to be in, and then develop models to predict, try to reconstruct this ECG and respiration signal. So our raw data is collected and transmitted either via Bluetooth or Wi-Fi. We have our IMU signal, we have our ECG signal, and then we have our strain forced respiration signal. The first step is determining the position of the collar. So that was done through looking at the IMU, specifically the Z-axis and the Y-axis. And here's the example of the dog sleeping on his right side. And then based on the magnitudes of these signals, you could place what position or orientation the collar was in. Then we had individual models for each of these locations, which were used to predict ECG and respiration. So step 1, try to determine the position of the collar. Step 2, apply the models to predict the ECG and the respiration for those positions. So for our ECG prediction, we utilize a deep neural network and create an individual model for each position. The data is normalized into smaller windows, and then the acceleration values are used to predict those reference ECG values. Our respiration prediction utilized a similar approach. However, we had larger windows due to the lower frequency of the respiration signal. So our expected heart rate range for the sleeping dog is about 85-pound Labrador Retriever. It's going to be 45 to 70 beats per minute, sleeping or resting. And the respiration range is generally in the 10 to 30 breaths per minute. So the evaluation for our system, so it definitely varies by position. So the best results tend to occur above the equator, where the equator is above. So 12 o'clock is the spine, 6 o'clock is the throat. So when on top of the dog, when the collar is sitting there, the IMU is sitting on top, we tend to get the best results with the highest F1 scores. And then more work definitely needs to be done underneath. So the poorer scores tend to occur down here at position 9. There's an F1 score of 0.728. So I hypothesized that when the collar is pressed underneath the dog and the surface, that some information is lost. Either it's damped due to the soft surface the dog is sleeping against, or it's not free to make those small micro movements of the heart rate. But overall, the results were pretty good on top, but there's definitely more work to be done in regards to the orientation and the results. For respiration prediction, so same setup. We see here, we have our reference signal and then our reconstructed IMU signal. Respiration is definitely more difficult to achieve from the system because you're no longer just looking at small pulses, but you're trying to see more macro movements along the neck and the throat. And we sort of had the opposite here, where instead of having lower results on 9, the lower results more came on the sides of the dog. So closer to the spine and close to the throat, but still had better results on top of the equator. So the conclusion for our work here, our overall objective was to try to extract these physiological parameters from our collar at multiple orientations. So we're already outfitting these razors with these collars. We already are set on collecting these behavioral and environmental. So the idea is while they have them, we're exploring the idea of can we do physiological monitoring of these dogs while they're resting or sleeping? And there's definitely the potential to do that. So the solution we had was we utilized our developed system, our previously validated platform against these commercial devices to try to estimate the heart rate and respiration rate utilizing neural networks. Our future work is definitely to continue to improve the models by collecting more data at the different orientations and to expand to multiple sleeping positions. So I don't have enough data to say for sure, but I definitely have a hunch that there's not an infinite space or infinite number of models required, that there's some overlap in depending on the position the dog is going to be, if the dog is sleeping on their left side versus sleeping on their right side, and which model is going to be appropriate. There can be some gray area between adjacent models, but as we continue to collect more data and look at the different postures, I believe that the space is not going to be infinite. There's going to be some finite number that will provide adequate results around. So long-term, once we're able to get specifically predict the heart rate and respiration rate, you're going to be able to look at welfare parameters such as heart rate variability, examine the activity level of the dog throughout the day because we're collecting that, and then looking at their sleeping and resting, and provide more information to guiding eyes and their raisers in how they care for their dogs, if their dog is energized and able to do more work, or if they need to scale back. So just collecting, it's opportunistic and collecting more information about the dogs while they're away from guiding eyes. So again, from Timothy, thank you to the National Science Foundation, our IBM Faculty Awards. Big thank you to Guiding Eyes for all their help and support in the projects. And thank you all for your attention.